Might just be because I'm so strong. Okay, so like I said, what we're going to talk about today is integrating through vector fields. Okay, and so remember kind of what we define a vector field as is for every point in space, we define a vector. A function assigns that point a vector. And we can think about it in two-dimensional space or three-dimensional space, kind of in five-dimensional. Mostly we think in two-dimensional space. So that's kind of how we are. So let's kind of think of like a good physical interpretation of this, like a good reason for why we want to do this. So what can you think of like something that would go along the path through a vector field that we might want to think about? First of all, what does integration do? Like kind of what is integrating do? It's an infinite sum. So we're kind of adding things up. Okay, so think of like when might we want to add up a bunch of values in a vector field? What do vector fields often represent? Yeah, so we can kind of think of them as like, a lot of times they apply to like topography or when we think of map making. But remember also we thought of vectors as being like a force field. A vector field we can kind of think of as representing a force field, like gravity or electromagnetic field or something like that. So it won't quite be the total force because we're doing line integrals, and so kind of what the physical interpretation is going to be is, remember way back in the day we looked at first how a vector in one direction does work along a vector in another direction, and so now we're going to kind of extend that and think about like a vector field doing work on a particle as it goes along the path. And then what we can do is use the integral to kind of figure out the total work. And so that's kind of what, if we have this particle moving along a path C through some vector field, and we can just kind of be general about the vector field for right now, then we can use the line integral to figure out what the kind of the total work done by that vector field is going to be on that particle. Okay, so let's kind of look at what that's going to look like. Okay, so I'm going to make this bigger. So, okay. Yeah, definitely. Well, I'm going to make those a lot shorter. They're not going to be as long, so I'm not going to kind of ramble so much. Okay, so kind of what we have to imagine is we have a path C that's going through space. Okay, so it's just kind of winding through space, maybe going like this. I don't really know. Okay, and remember a vector field assigns to every single point. It assigns kind of a specific vector. And so what that would look like is that if we have a point here on our curve, then that's going to have a specific vector assigned to it. Okay? And remember, they can kind of go however they want. Well, that's actually... Yeah, so that's going to be the way the particle is moving. Okay, so in other words, we kind of like pick some point here on our curve that's like x, y, and z. And so x, y, and z lies on the curve x, y, and z, not x, y, and y. X, y, and z is on our curve C. And so this blue vector right here would be f of x, y, z. X, y, z. Something like that. Okay? And so it's just kind of some vector. It just assigns at some point, some direction, and some magnitude. And then, but you were kind of going in the right path, thinking in the right direction, thinking about the same thing. Because we remember way back in the day when we want to figure out how much some given vector is doing work in another direction. Does anyone remember how to do that? Yeah, the dot product. Okay, so in other words, we're going to kind of think of taking the tangent vector here. Kind of cramped up. This is our tangent vector. And that's the direction of the particle. Okay? And so what that means is the work done by our force F at our point x, y, z. We can approximate that work by taking the dot product of that force vector and the tangent vector. Okay, so that's kind of what it all comes down to. And then we can think of, well, going back to our integrating infinite sums, we can, if we break each of these into little pieces and get a sample point from each one, take the limit and sum them up, it'll end up kind of taking into the integral. Okay? And so, this is what it kind of looks like when we put it into integrals. We're going to get this length element here, because we're breaking it into little delta s's. But we're just going to have a dot product of the force vector and that tangent vector. And so when we kind of take the limit and sum them all up, we're going to get what we call this like line integral through a force field. And so notice all it is the dot product of the force field and the tangent vector. And so this is the tangent vector for C. Yeah, so that's like the tangent along that curve. C, where we just have some parameterization. Okay? Oh,